Thanks everyone for joining from all over the world. It's exciting. This is our August meetup, and we do have, I might say, a multimodal special going on today, right? We have a lot of topics here today. I'm gonna kick it off here in a bit, talking about some recent advancements in multimodal Gen AI, specifically the segment anything model by Meta, which is super exciting. I'm gonna have a couple of demos there as well. Then Shelbee will show us how to fine-tune multimodal models. And then Chris, you're going to show us some what's the true here? True multimodal RAG. Is there not true?
There is what I consider to be true multimodal is an any to any. So any format to any other format. So audio, video, text, image. Yeah. So most of and I just posted a quick audience poll here. Just have it up for like 1 minute total. Just want to get a rough idea of what folks are doing out there with multimodal. Yeah, the sort of what I would call fake multimodal is where you convert everything into text. So there's that extra step where you have to convert the image, video, or something, get a caption summary of it from some model, and then you store that in the vector database. So we're going to throw all that stuff away and talk about true any-to-any multimodal RAG today.
All right, good to know the true stuff today. All right, again, here is just a quick run through. Also, we're going to record today's meetup, just a little bit of housekeeping, and we're going to post the recording to our YouTube channel. And Chris, you can maybe put the link here in the chat for everyone. While I'm also making another public service announcement, we do have 2 in-person specials this month coming up as well next week. One is our own Generative AI and AWS Meetup special at the AWS Loft in San Francisco. So if you are local to the Bay Area, local to San Francisco, you might want to check this out. We're gonna talk a little bit more about multimodality. It's so exciting. So we're gonna talk about how to build XR application, mixed reality, extended reality, with a guest speaker from Meta, from their Immersion Labs. So that's going to be super exciting. We're going to learn about agentic code interpreters, and also going to see how to integrate multimodal RAG into a larger conversational AI assistant. So a lot of great topics at the AWS Loft on Market Street in San Francisco next week, Tuesday. And my team at AWS, the developer relations team, we're also organizing another meetup on the Thursday next week. Bits, Blocks, and Brawls, fun title. We're gonna show how to embed agents, assistants in games. So it's gonna be focused a little bit more fun on how to use Gen AI and do some fun gaming exercises there. So if you are local again and you have some time, it's going to be evening meetups. So we're going to start, doors open around 5 p.m. If you want to join us, you can check out, and I'll put in the links here in the chat as well in a bit, for our meetup via Luma. And then you can RSVP for the DevRel team meetup on Thursday via the Amazon side. And let me just quickly grab the links here and then also put them in the chat, and then we get going here. All right, here you have the links if you're interested. Perfect. And with that, let's get into the first talk of today. So I want to walk you briefly through what's been happening in the multimodal Gen AI space. And here's a little timeline you can see. There's been a lot going on. It's not complete, but I think just a couple of the highlights we've been seeing, and which I definitely think are worth calling out. CLIP is still very important. CLIP is not new. CLIP has been around for a couple of years now. It was introduced by OpenAI in January 2021. CLIP stands for Contrastive Language Image Pre-training. And what CLIP does, it bridges the gap between visual and textual understanding. And it's really been kind of a game changer for zero-shot learning. And it helps AI to understand and categorize images without direct supervision. CLIP is still heavily used up to this day, But there's been a lot going on after that. We had diffusion transformers coming out in 2022 by researchers at UC Berkeley and New York University. And diffusion transformers replaced the convolution-based unit architecture that has been around with transformer architectures. And this helped to improve the image and video quality in generation. So also super exciting. And then you can see here in red, the segment anything model, short SAM, got released by Meta in April 2023. And I'm going to show you a demo here in a bit as well, and just a brief overview of the architecture. But SAM really, really helped to advance specifically the field of image segmentation with a very precise and versatile image understanding that they implemented. Then just a brief REST overview here. In April 2023, Microsoft released a visual instruction tuned model called LLaVA, or Large Language and Vision Assistant. And think of LLaVA as an end-to-end trained large multimodal model that connects a vision encoder to an LLM for general purpose visual and language understanding tasks. And LLaVA was trained with pairs of language and image instruction tuned data. So this is really kind of an interesting case as well. Then another big one, I think, soon after was ImageBind. ImageBind launched in May 2023. And what ImageBind does is to include a wide range of modalities, image, text, audio, others, and binds them all in with the image, which is super exciting and which is a new kind of approach. So all the modalities are bound back to the image there. And then OpenAI, a few months later, launched the closed source GPT-4V vision model. And this one is now, I think, deprecated and integrated into the GPT-4o model. Then we had Chameleon. Chameleon was launched and introduced in May 2024. And it's also kind of unique in a way that it is designed really to be flexible and allows a wide range of tasks across different modalities, super efficient as well. And then just recently in July, Segment Anything 2 came out by Meta, which builds on the original image segmentation model, version 1, but now also includes video segmentation. So you can have, basically, you can track an object through the video. All right, this is just a really, really brief, short timeline. There's been much more going on in the space, but those are, I think, a couple of the ones that are super, super interesting to look deeper across the different tasks. All right, let's go straight into the segment anything model, SAM 1 and 2. The first model, segment anything, was developed as a foundation model, and they developed a new task which they called promptable image segmentation, which allows for segmentation of any object in an image using simple prompts. And you can see a couple of those prompts here. It could be points where you select a range in the image. It could be boxes, or it could be masks. SAM uses a transformer-based architecture, which enables it to generate segmentation masks in response to those user prompts. The model was trained on a large data set of annotated images, which helps the model also to generalize really, really well to unseen images. And just some of the highlights of the model include the zero-shot performance. SAM1 is really capable, and it's really amazing how it does it, of zero-shot segmentation, meaning you see an image, you share an image, and you point it to the object which you want to segment. And even with data it hasn't seen before, and it does a really, really great job there. The flexible prompts I already mentioned, so points, boxes, entire masks, and also it has a really impressive speed and accuracy, which makes it really suitable also for real-time applications. Now, if we look a little bit and zoom into the architecture of the SAM model, I mentioned it uses a transformer-based architecture, in specific a vision transformer that runs once per image and then outputs an image embedding. It also has a prompt encoder that embeds the input prompts, such as the points, the clicks, or boxes that you share. And then there is a lightweight transformer-based mask decoder that then ultimately predicts the object masks from the image embedding and the prompt embeddings. And with that said, best thing is to do a quick demo and to show you how this works. So here we are on the website. I'll zoom in here a little bit as well. Segment Anything by Meta AI. And I'm going to click here to start a demo. So this is Segment Anything Model 1. And I'm just going to select, let's do the cats. We talked about dogs this morning. So let's do some cats here for a little bit of diversity. All right, so you see an image here. And what you can do is simply click on objects. So you can already see how the color flips. So I can click on this cat. And it's done a pretty amazing job in, you can see, finding the mask for it. You can add another cat here. You see I'm adding those points by clicking on it. And I can say which parts of this image I want to segment. You can select here on the left. So I'm clicking next, I'm selecting box. You can also do traditional bounding boxes. So I'm drawing a box here around cats. And you see how the image gets segmented now by what I select. Also interesting, there is a feature where you can say, okay, segment literally everything in this image. So if I do that, you can see how those points get layered over the image. And now what the model does is really try to understand each and every segment in this image. And now you have everything segmented. So a lot of use cases, a lot of applications, and it's really great how easy it is with Segment Anything here to run image segmentation, especially thinking back in the old days with the first image segmentation models. I think a lot of us have been using. So this is really kind of delightful, just clicking there with a point and then having the right object mask. All right, let's go back and let's have a look at Segment Anything SAM 2. So Meta didn't stop here. So just recently in July, they launched Segment Anything 2. And they're building SAM 2 and they extend the capabilities of the first model, but they're introducing another task they've been training the model for, which is now promptable visual segmentation. They call it PVS for both images and video. So this is really amazing. The model tries to understand the complexities and helps you to segment an object across the video frames. So you can basically track it throughout the video. And this is not an easy task, right? This includes challenges like motion, occlusion, varying lighting conditions in there. Looking at the architecture, what they did to implement this, they built upon the transformer architecture from the first generation model. But now they also add a new component, a streaming memory mechanism that allows it to segment those objects across the video frames by storing and utilizing information from the previous frame. So it keeps this memory of where the object has been seen before. And there's also the case, the object that you're tracking might get out of the frame. So it might not be visible in certain frames and then pop in later, right? Like imagine the cat running out of the video and later running back in. And also to achieve this and to get this quality, Meta used and generated a large-scale video data set. So the data set also has been released, which is really amazing. So especially for research to pick up and keep building on that. So looking at the architecture, I mentioned a couple of things already. It's a unified model for images and video. So it can handle both single image and video segmentation task. And for the video segmentation, what happens, it basically treats every single frame in there. Then it also comes with an image and video encoder that processes the frames sequentially. The streaming memory that I called out. So this is a memory attention module that enables it again to maintain the context about a segmented object over time. And then it has this interactive data engine which is a new data collection process Meta created to iteratively improve the model performance and basically help to create this big and diverse data set. All right, with that, let's do another demo here. So I'll jump here into the Meta Segment Anything Model 2 demo on the website, try the demo. And let's load it up and let's see how the video performs. All right, so here is a sample video. And I'm selecting here an object. So let's select the soccer ball here. And maybe the two shoes, right? Let's see how that works. And then I'll select here track objects. And now you can see here in this video how the ball and the shoes getting tracked, which is really impressive. You can start over. You can change the video. So let's see what they have here. Let's do this ocean here. What do you call it? Is it a squid? So what I can do here, let's track this and let's see how this works. And this is really amazing if you look at the motions here. All right. You can also overlay and get some more effects going on here. Just do a surprise me here, like a starburst effect, or you can do, what else is good? Spotlight here that follows the object. So really amazing what they can do with this segment anything model. All right. And just a couple of highlights here from the training process and the data set. Again, the model was trained on both image and video data to achieve this, and using interactive prompts to refine the segmentation masks across the video frames. They used the training data from the first model on static images, and then they fine-tuned in a second stage the model on the video data. The data engine that I called out was developed to help develop this data set, and they had 3 phases in here. They started with manual annotation, and then they integrated the model into the loop to have a more efficient mask propagation and annotation refinement. So basically, first manual annotation, then it was kind of a hybrid with a model, and then the last stage was completely automated by the model annotating. The data set has roughly 50,000 videos and over 600,000 what they call the masklets. And this data set is really, really large. So if you compare it to available data sets in this space, I think it's around, they claim 53 times larger than an existing video segmentation data set. So really exciting. And great performance, real-time processing capabilities, which is super important to, obviously, for video and embedded in real-time applications. It opens up a broad range of applications where you can use it. And it's available under the Apache 2 license, which is also really cool. So you can check it out here on GitHub. And I'm also going to post here, again, the links in the chat if Chris hasn't done so. Segment anything papers and the demos available online if you want to play around with it as well. And that was a quick intro here to the recent advancements in the segment anything model. I'll check in the chat for any questions. Chris, do you want to call out any questions here to address? And then Shelbee can get ready to take it away for the next talk. Any questions?
Yeah, I think I've been, there, as Max pointed out, there's distilled versions of SAM that are, smaller RAM to fit these on edge devices. There's gonna be some questions coming in. We are really short on time today, so let's answer those, I think, offline here. And Shelbee, are you ready? These are like really good questions, but we'll answer them in the chat.
Yeah, I'll have a look in the chat.
Yep, I am ready. Let me know if you can see my screen okay.
Can
Yeah.
see it. Yep.
All right. So going back to the book a little bit and all of the code examples that actually kind of demonstrate these different like fine-tuning techniques that we'll talk about or model customization techniques are in the GitHub link, and I'll post that after this. But we do have example code in there. So in the book, we actually focus quite a bit on diffusion-based architectures for multimodal, and they're popular in multi-models like, you know, Dolly, Midjourney, Stable Diffusion, and we do go into quite a bit of detail on Stable Diffusion in terms of the architecture behind different Stable Diffusion versions, as well as in general kind of diffusion-based models. So inside the book here, this is just kind of a layout, right? So we do talk in chapter 10, we talk a lot about the architecture of, you know, diffusion-based models, as well as like stable diffusion architectures, but also ways that you can control or customize the output of an image based on kind of prompting alone. So we talk about that quite a bit in chapter 10, but for this specific talk, we're going to talk a little bit more about fine-tuning. And some of the things when we go into fine-tuning that are beneficial is kind of really understanding the diffusion architecture, the fundamentals of diffusion architecture, right? So you have forward diffusion, which is the process of basically adding noise to an image. We have reverse diffusion, which is, interestingly enough, the exact opposite process, right? So where you're training a noise predictor to then remove noise from that image and then generate an image. We also go a little bit into UNet as well. So the UNet architecture, which you know, relies a lot on these multimodal models like Stable Diffusion. Basically, there's different encoders, right, where you're going through forward diffusion, reverse diffusion through this, like training this new noise predictor as part of it. And then we kind of go through the different components of a UNet architecture within there. But that being said, I know we're going to talk more about fine-tuning in this particular talk, and to kind of stay with time. In chapter 11, we talk more about fine-tuning, right? So we start with probably the lightest weight method, if you will, which is ControlNet. So with ControlNet, you're not necessarily touching the model as is. So you're not touching that base multimodal foundation model. You're actually using these pre-trained, or you can train your own deep neural networks that are trained for specific tasks, whether it's like edge detection or mapping the depth of objects within an image based on that set of inputs. So one of the benefits there is you're not training an additional model, right? You're training these smaller controls, if you will, or utilizing existing controls out of the box, which is what we kind of demonstrate a little bit more inside the book in terms of utilizing some existing pre-trained controls. And one of the ones that we talk about is edge detection. So if you look at, and there's a bunch of pre-trained controls out there that you can utilize, but if we look at edge detection as a specific use case, showing kind of this car picture here, what edge detection will do is basically translate that image into the edges of the object, right? So it's going to look at the object, identify or detect the images or the edges of that image within the object, and then basically create a canny edge map for that image. And canny edge detection isn't necessarily new, right? It's been around since a long time, I guess probably the 80s or something. But the novelty in this particular case is really about combining that with these multimodal models like Stable Diffusion, so that essentially, if you look at this example, what we're doing is we're using the control of the canny edge map to take that image, detect the edges within that image, which then will use this canny edge map image that's generated and feed that into a Stable Diffusion model using a prompt, right? So basically, how do we fill out the edges within that image? So in this particular case here, you can see we're saying, you know, a metal orange colored car, complete car, color photo. So prompting the model based on that canny edge map, how you want the model to then generate an image using the prompt controls that you've kind of defined within here. So if we look at that, you can see basically this is kind of the newly generated image. And this is using a base Stable diffusion foundation model as is. It's not touching the original model, but using in this case, it's a pre-trained out-of-the-box control that takes that original image on input, which is that blue car, does the canny edge map for that, and then creates the newly generated image based on the input prompt. So pretty lightweight way to customize the model in a way that's not touching the original model, but you're still able to customize the output image that model creates by combining the pre-trained control neural net with the original foundation model. So the other method we talk about is fine-tuning itself. So in the case of fine-tuning, here we're really talking about full fine-tuning, if you will, which is actually updating the full model. So a common technique here is DreamBooth, which is the one that we have some code samples for inside the repository. But also what we're doing essentially with DreamBooth is we are basically taking a set of images. You can do it with 3 to 5. Sometimes that can be some overfitting can happen, and we can talk about some ways that you deal with some overfitting in that case. But with a smaller number of images, basically, and using that to then customize a model like Stable Diffusion to generate an image that can now be created based on images it wasn't originally trained on, right? So in this case, it's a picture of, this is actually my dog, Molly. She's very sweet. She's also very bad. But basically using a set of images, you can customize the foundation model with a unique identifier. In this case, the unique identifier was Molly. And in this case, we combined it with a class. You don't have to do that, right? So a class of dog. And with the prompt photo of Molly dog, what that does is, takes the images, goes through image encoding, the text goes through text encoding, and then you're able to train the model based on that set of images so that now when we prompt the model the next time for create an image of Molly in a particular setting, we actually have a model that understands who Molly is, what Molly looks like, and is able to produce output that includes Molly. I talked about overfitting, right? So that's a pretty common problem or challenge is overfitting for Molly. So some things that can be done there is a concept called the preservation. So what that does is basically, in addition to Molly's images that are input for fine tuning, we have a set of images that are under that same class of dog too, right? So that way, not every dog image is of Molly, right? Molly is associated with the unique identifier that was used during fine tuning, but Molly isn't the dog that should be outputted every time, right? So we're combining our custom images of Molly along with just class training images of the class dog in combination in fine tuning. So that's something you can do to control overfitting on some of this stuff. And then, like you mentioned, like I mentioned before, when we're prompting the model, we use that unique identifier in our prompt. So Molly in this case, right? Molly dog is the unique identifier, and we're basically using that fine-tuned model now to actually generate images of Molly in different settings. And in this case, like I said before, like the downside of this, the plus side is it creates really good images. The downside is it does result in a brand new model, which, for Stable Diffusion, I mean, it's not massive, right? I think it's roughly, 5 gigabytes or so, but still it does result in a new fine-tuned model each time. So the downside would be storage and compute, of course. So the other method that we do talk about inside here is DreamBooth along with PEFT and LoRa. So similar to, I know we've talked about parameter efficient fine tuning before, and specifically LoRa using low-reg adaptation matrices, right, to fine-tune essentially adapter layers, if you will. So in this case, what we're doing is we're combining DreamBooth fine-tuning along with PEFT LoRa. So what that allows us to do basically is train these adapter layers. They're small layers, and they're applied to the cross-attention layers. And if we went into the diffusion architecture, which I could do, I'm trying to speed it up a little bit, but if you look at the diffusion architecture, specifically when we dive into Stable Diffusion's architecture, there's these cross-attention layers within it that relate the image representations or the image encodings with the text encodings or the prompts that describe them. So what we're doing in this case with these adapter layers is we're actually training those cross-attention layers only, and then allowing the rest of the, in this case, stable diffusion model to remain frozen. So similar benefits that you get for parameter efficient fine tuning on an LLM, where it's more, storage effective, compute effective by training only those small adapter layers. And you can see inside here, basically doing a similar thing, but we're only training those adapter layers that then get essentially merged with the base foundation model when you're performing inference. So this is Molly Dog on a beach. Doesn't quite look exactly like her. This was done against an older version of stable diffusion, sorry. And then finally, textual inversion. So we talk about, there's different methods for fine-tuning these models. We really do dive more so into Dream Booth, right, which we just went through. Laura, along with Dream Booth, and then textual inversion. There are other methods. There's like hyper networks, which we don't necessarily touch on inside here. But in terms of this third version of fine tuning, it works very similar to the way Dream Booth works, where you have in the case of Dream Booth, you're using this unique identifier, right? So in that case, we had Molly. With textual inversion, you're also training a unique identifier, which they actually refer to as a pseudo word. So in this case, we have, I'm going to put up the picture, M asterisk as our pseudo word. The main difference between textual inversion and Dream Booth is basically the setup's pretty unique, are the same, like I said. So what we're trying to do in both cases is associate that unique word or pseudo word or unique identifier with our training images, right? So using that diffusion process. But in this case, in the case of Dream Booth during the diffusion process, we're actually calculating a loss of we're calculating the loss, right? So as we're going through and denoising that training image, we're calculating loss against what that image should look like, right? On an image that isn't denoised. And we're calculating that loss, but during Dream Booth, we're actually going back and updating the model as we calculate that loss until we get to the results that we need. In converse to that, with textual inversion, we're not updating the model. What we're updating is the embeddings, the text embeddings of that pseudo word. So in this case, with textual inversion, it ends up being lighter weight because it's not a new model, but it's a new trained pseudo word. So the textual embedding of those pseudo word that you're creating is actually what we're calculating and we're training over time. So it's lighter weight than Dream Booth. However, Dream Booth is typically, I would say, more broadly used, right? Because of the results typically. And this kind of just goes through another code example within there. And like I said, these are actually inside the GitHub repo as well. So I'll post a link to that GitHub repo so you can check out the code examples directly, play with those a little bit. And then let me see. Yeah, so you can see this is kind of the result with textual inversion. So I think that was all that was targeted to go through for today. But any questions while I think we still have 4 minutes. Or I can give the time to Chris too.
Thanks, Shelbee.
Okay, I think for time's sake, we're going to go through, we did post links to the book, where this is coming from, and just, quick reminder that this recording will go on YouTube. Okay, thanks, Shelbee. That's awesome. Just quick question. Yeah, how long did it take you to write this chapter?
A really long time. Probably longer than it should have. Yeah, really long time trying to dive into the architectures, especially across the different versions of the model, the base architectures. Yeah, it was a few.
Gotcha. Yeah, and I remember the O'Reilly folks kept coming back to us with like more questions, more and more questions. But this was a big reason why we did so this book, we specifically targeted multimodal, even though we wrote this in 2023, right? Was this 2024? So yeah, the O'Reilly folks also agreed with us that we should be covering multimodal and not just LLM. So this was a really exciting chapter. And also, Antje, you in chapter 12, do we have multimodal in there for Bedrock? I think we have a couple examples, right?
I think we just have, yeah, we have image generation, I think.
Yeah.
Okay. And since the book was launched, there's now a Amazon Titan multimodal embedding model, which I'm going to cover, I have a slide on here and how it works with OpenSearch and things like that. So there's a lot of cool stuff you can do now, all within the Amazon ecosystem, AWS ecosystem.
That is right.
Okay, sweet. There's a couple other chapters where we talk about multimodal too, I think, but this is chapter 10 covers multimodal as well. We broke multimodal up into 10 and 11, right? Yeah.
Yeah.
Is 10 where you go?
10 is
the
foundation where we talk a lot about the diffusion-based architectures and go through the architecture specifically, or diffusion-based architectures, but also like Stable Diffusion 2, Stable Diffusion XL architecture, the differences between those, how they work.
There's been a few questions throughout the talk about the resources needed. So I'm going to point everyone to this GitHub repo. This actually has the code that we ran to generate these examples. And so if you're wondering about which GPUs that we used and everything, it's all covered in there. I mean, I think for the most part, we had the most success with the A100s, which is P4D and P4DE, which has 80 gigs. Depending on the size of the model that you use, if it's 8 billion or if it's 70 billion, will dictate that. But and the size of your data set, the size of the batches and all that stuff. So okay, Shelbee, anything else?
No, I think that's it.
Great. Let me grab my screen. I think there's one or two questions in there.
Yeah, I'll take a look at the chat and
take a look at those. If you do have to go, Shelbee, feel free to hop too. You can, I know you're just getting back from vacation. Okay, let me share my screen. I got the right screen. Can you see my screen?
Yes.
Cool, cool. Okay, so get rid of that, get rid of that. All right, here's the code that we're going to go through. I was trying to get Max's demo to work. I didn't get it fully working. I have to get the Docker stuff going, but I've got some slides and I've got my demo, which is exciting here. So let me get this. All right, we have a lot to cover here. Let's see, in 20 minutes, 19 minutes. So, and I do have a fun demo that I'm going to show. The idea here is, and I kind of informally call this true multimodal, in that we're not converting everything into text and then just storing these with text. So that's kind of the traditional multimodal RAG that you might see, where you have an image and you have text and you're trying to project those into the same embedding space. And Clip is very good at that. So we'll talk about Clip, but we're going to go beyond Clip and talk about ImageBind, which actually came out last year. And there's some It's a little tricky to get working if you're trying to do it on your own. There's a Facebook implementation because it comes from Meta, but it's a little bit wonky and doesn't work all the time. But in the demo, I'll show how to use Weaviate, which is one of my favorite vector stores. And then also Max, who posted his demo, looks like he's using Chroma. So you can use Chroma with ImageBind as well too. We'll also talk about, the sort of any-to-any multimodal RAG. That's what I call true RAG, where you can go from, audio to video. You can go from, video to text. You can go any type of, what's called cross-modal retrieval, right? And of course, at the foundation here is multimodal embedding. So the ability to have one unified joint embedding space that can support all of these different modalities. So Antje mentioned CLIP, Shelbee mentioned CLIP. CLIP is really the key building block for a lot of these multimodal systems. I'll show when we get to ImageBind how you can actually swap out CLIP for ImageBind. You can just do a drop-in replacement and typically expand the number of modalities. So CLIP is focused on images with a vision transformer and text only. When you swap in ImageBind, now you have the ability to go to audio and other video types of modalities. There is an open CLIP implementation. It's worth pointing out that CLIP was created and first documented by the folks over at OpenAI back before they had ChatGPT. We see Ilya here, the famous Ilya Sutskever on here. So I don't think he's at OpenAI anymore. He's off doing his secure and safe intelligence or something company. So, but yeah, all this stuff comes out of OpenAI. They do have a CLIP model that you can access through the OpenAI API. However, there's also an open source implementation that's called OpenClip. Okay. The key here is that we are unifying vision and text encoders, okay? And VIT, by the way, is a common acronym for Vision Transformer. And so you'll see these are some of the top performing models right now. I actually just took a screenshot last night. These are the top performing models and the different data sets that they've been trained on. If you've heard of Leon, that's actually a very common data set, and there's multiple variants of these. So some of the customers that I'm working with use a combination of the Leon or Leon, yeah, not sure how you say it, and then combine it with like Llama 2, Llama 3 on the text side. Okay, so and this is very useful for these, quote unquote, multimodal RAG use cases. But again, this is just image and this is just text. So the idea here is you would use CLIP to generate the embeddings for those two different modalities, and they will end up in, near each other in the embedding space. Okay, so here's the image encoder, here's the text encoder. I think Shelbee showed this image earlier, and the separate encoders, and then it all comes back down to cosine similarity, our favorite mathematical function here, where we take one embedding space from the image and the other embedding space from text, and we can find how similar they are. Okay, now that's assumed that this has been trained, that CLIP has been trained on these two different modalities and has unified these embedding vectors. Okay, and when you're training CLIP, what's happening here is you're basically training to predict whether or not a particular caption or text is going to be near this image. And so think of web data. This has been trained on lots and lots of public web data where we have images on a web page that are right next to some text. And so there's a high likelihood that that text is right, like referring or describing that particular image. It's not always the case. This is where you have to do a fair amount of data cleansing, but you can assume if there's like a figure 1 or something description that does associate. So for example, figure 10-21, how CLIP is trained using image and text pairs likely describes what's going on in this image. So those will end up near each other in this embedding space. Now, The C and L in CLIP stands for contrastive learning. And this is a technique that essentially will pull these image embeddings towards the related text embeddings. At the same time, it's being trained to push these images far from the unrelated text in this embedding space. Okay, so very important technique, ends up with a joint embedding space as we see here, text encoder, image encoder, okay? Real quick side note, yeah, as I mentioned, the end of last year, I think it was reInvent last year, so 2023, Amazon Titan did release a multimodal embedding model. These are relatively rare. You know, like I said, yeah, OpenAI has one that they offer through their API. OpenClip has a whole bunch of them, but there's one, and so trying to find these is actually not very straightforward. So just note that there is one, you can access it through Bedrock. You could pass both text and image. There's also this integration now with like OpenSearch as of this year, I think as of OpenSearch 2.11 or 2.13 something, where you can call out to OpenAI, call out to Amazon, call out to Anthropic and give it the query text and the query image. My hunch, and I actually don't know the details of how this embedding model was created, but my hunch is that it is likely CLIP based because it does only handle text and image right now. All right, let's expand to talk about this ImageBind. So think of like ImageBind as like, you know, CLIP 2.0, and we can now expand into audio and video. This is the demo I'm going to show. There's also ways to pass in IMU data, which is like velocity, acceleration, rotation, so, you know, gyroscopic. You can also pass in depth images and thermal images. There's a really, so yeah, this is all very well documented in the ImageBind paper. All of this is based on transformers right now, and they're used to encode each of these modalities. And what's going to happen is once the modalities are encoded, they're then projected into the same embedding space. And so all that magic happens with the ImageBind. What's really cool now is we have this multimodal embedding space, and but keep in mind that when this was trained, it was not trained on this Cartesian explosion of text image, you know, text video, text audio, text depth, like this, you know, sort of exponential explosion of data. And it's because we don't have a lot of examples in the real world that can unify all of these different, you know, 6, 7 modalities, right? So what's really unique about ImageBind is there's emergence behavior that was shown where if we only pass in text image, video image, audio image, depth image, you know, thermal image, if we combine everything to this image space, right, which is what the ImageBind, yes, that's where that name comes from. There's this property where we can actually find, you know, pairs of modalities that were not explicitly trained. Okay, so I can pass in a you know, depth image or a thermal image, and I can get back text, right? Even though those two weren't explicitly passed in during training. So this sort of yes, I think of it like an extra hop, right? So I can get from, you know, video to text through this joint embedding space where maybe I didn't have a lot of video text samples or, you know, video thermal, let's say, okay? So pretty cool. This is useful again because we do lack training data that spans all of these modalities, consistently spans all of these modalities. There are very few rows of data that have text, video, audio, depth, image, and, you know, thermal and IMU data all in a single row of training data. So that was really the big breakthrough with this model was if we combined everything to an image, then things work out. So here is a sample, and here's, you know, so this is actually trying to get the ImageBind code itself, this library, which is actually a little bit tricky to install. And here's where we're crossing these embeddings. So, vision cross with text, audio cross with text, and then vision cross with audio. Okay. So some pretty simple code. You can find this out there. It's pretty Googleable. It'll be on, I believe, the GitHub, the Facebook research GitHub. Okay. And so this is what's going to allow us to do multimodal embedding space math, right? The arithmetic here. So if you're familiar with the, king, queen, man, woman sort of vector space, mathematics, that's what is happening here, but in a multimodal sense because of these like ImageBind embeddings. We can also do advanced like image generation. We could do better segmentation, and I'll show how you can actually take SAM1 or SAM2 and drop in ImageBind and make it more multimodal, expand beyond just text and then images or video and then images. Okay. And this is what gives us the ability to do the any-to-any search, what I call true multimodal, all these different variants here. So here's a cool example where you can pass in an image of a bird, you can pass in sound of waves and get back images with birds that are near waves or near water. Okay, so kind of cool. Let's talk about the image generation segmentation. So this is where we can swap out clip, put in ImageBind. There's no retraining required, just drop in replacement. We can actually modify DALL-E or Stable Diffusion to now take audio or now take thermal or take, some other type of stuff. So here we have the audio of a dog, and it can produce and generate a image of a dog. And I'll show an example of this here in a bit. The other thing is we can modify segment anything model, SAM1, SAM2, to use ImageBind. And we can now then detect objects based on audio, other types. Yeah, so this paper really likes audio because it's not image, it's not video, right? And it's not text. And then, of course, the any-to-any search, we can retrieve objects that are similar to any modality. So I can pass in audio and I can get back basically anything that's in my vector store. All right, let me quickly show the demo here. And I believe I mentioned this earlier, but I am using Weaviate today. They have really good support for, and this example is in that same repo. This example is here. Let me paste it into the chat. Here is this example. And the data should be in there as well too, so this should run out of the box if you follow everything. So at some point, you do have to do a Docker compose. This is going to bring up the Weaviate server, the vector store on your machine or your cluster. You want to install the Python client here, pip install. You're going to connect to local, check if it's ready, get the metadata. Here we see that the multi-to-vec -bind, this is ImageBind, has been registered. And it's worth pointing out that you could just use multi-to-vec, and that is going to be clip-based, right? And so these are modules that are named and specific to Weaviate, but here's what they're using beneath the covers, which is multi-to-vec is just image and text, and that's clip-based. Multi-to-vec bind, we've swapped out clip for the ImageBind. And keep going through. We create our index. We're going to give it different. So here we're going to use audio, image, and video. Convenience function to convert things into base 64. When you start doing multimodal, you need to get very familiar with this base 64 encode decode. We've got a bunch of images here that I have prepared. And we've got, bird audio and cat videos and dog videos and meerkat. So we got we have audio, we have images, and we have videos. Okay, so we insert all the images here, then we insert all of the sound. Pretty straightforward. We're doing batches just to speed it up a little bit. We're then telling it to aggregate. That's a Weaviate way of pulling everything together, making sense of all this. And now we're going to, okay, that's the video. And here we see that we've got 3 groups. We have image, audio, video. So this vector store has the metadata to know whether or not the media type is image, is audio, is video, but it's still projecting all of these into a unified joint embedding space. Okay, and then now this is the real fun. This is going to be the like any to any multimodal search, what I call true multimodal search. Those are a bunch of helper functions, so I'm just going to skip past those. And we're going to say query this index with this text and get me everything back that you see. So a dog with a stick. This is going to bring back video of this dog. So that's cute. And then we've got audio of this dog, and we've got a picture of a dog. So obviously this is sorted by relevancy. And what we see here is that the video of a dog with a stick is the most relevant, but it also does bring back other modalities that are in similar vector space, thanks to ImageBind. Okay, a few other dogs here. This is my favorite. Pre-kisses, kind of cute. Let me zoom out here. And I am in the search for a puppy, if anyone has a good recommendation there. Here we got some cats, everyone's favorite. And oh, what was the query here? Image. Okay, we're just showing the cat. Gotcha. Okay, so this is what we're searching for, is this cat. And find us any, so this is the query. Querying near the image, bring back the top 3. And that's a cat that's similar. There's another grumpy cat. And that's a scary looking cat. Okay. And then we're going to do audio. So this is audio of a dog. And coming back, we get audio of a dog with a similar bark. We get a dog with a stick. And then we get other dogs as well too. And of course, no multimodal can be complete without searching for a video of a meerkat. And so here we are, and we're going to get back other videos of meerkats. Looks like first there, then we get images, and then we get more of these images. So that's my demo there. And okay, Antje, I think we're right at the top of the hour, but do we have any questions?
We had a really great discussion going on, still going on. I think the benefit of all combining it in a joint embedding space versus doing it separately and then concatenate embeddings. So a lively discussion here. And we kind of need the correlation between the modalities here to kind of are able to make this type of queries here, right?
Yeah. Yeah. So everything is being bound to the image space, right? And that has proven, so as opposed to essentially binding everything to the text space, you know, using textual descriptions. So without true multimodal, we have to convert everything into text. And usually we're passing this to an LLM that can handle images and say, you know, describe this particular image, or like describe this video, or, you know, describe this PDF. And that will very naturally lose some of the nuance of the image because it's just going to describe it at a high level, but it's not actually able to do the sort of pixel level or the patching, right? So patches of these images become the tokens. So just like we have tokens in language, which are words or, you know, partial words, we now have patches of these like images that are, you know, being used to compare and like to do the embeddings. And
Right.
so, yeah, yes, go ahead.
We have another question here, which I think goes more into the understanding of the content in there, right? Like, let's assume we have a graph in the image. Could I ask it, you know, at which x-axis, what is the value of y and stuff? So I think that goes more into parsing the content and understanding it,
Yeah.
versus you are showing like a RAG use case, like finding stuff near.
Right. Think of it like I can So this is really focused on the retrieval. And then I guess probably what would be the next step is to show what's being retrieved. I can pass that in now to a model that can then do visual question answer. So first step is, right, so what that person's talking about is typically visual question answer, the ability to summarize tables, to answer questions about financial statements and things like that. When it comes to PDFs, we have a bunch of examples, I think, with PDFs, and in that 10 underscore multimodal from the book, we actually have examples in here about visual question answer. The models at the time, which was like 9 months ago, 10 months ago, were not super good about like financials and adding, and I mean the whole space has changed since then, so these models can actually add a lot better now. But yeah, I think what you would first do is retrieve things that are similar, and then you would pass that into the next part of the so RAG, obviously this is the retrieval step, then you're going to augment your prompt and then going to generate some response based on that. So
Okay. Question about the GPUs. I think this is kind of a tough question here for everyone. How much GPUs would you need, right? What is the RAG architecture multimodals? Yeah.
Yeah, I'm actually not using GPUs for this demo. However, this is a very small data set, just 3 to 5. I will say ingesting took a little bit longer than I thought it was going to take. Let me see, where did I ingest? So you will definitely benefit from GPUs. The more memory that you have, the better. So that would be in Amazon speak, that would be P4DE and P5s. A little tough to get a hold, but I don't have a timing here, but these videos probably took about 3 or 4 minutes, and it's only 6 videos, and I'm on an M3 MacBook here. So yeah, during the ingest phase is really where most of the processing is happening. Once it's in the embedding space, then it's a fairly quick, cosine similarity. But yeah, and then if you're trying to search on a whole bunch of videos at the same time, there'll be some processing there because it has to take the video that it hasn't seen. So yeah, obviously the more GPUs you have, the better. All right, I do have to go, but I think I'll try to answer the other questions here. Yeah, Antje, do you have these questions somewhere? And then we'll do... Yeah. Post a link. So here, we're going to post the video to here. And here's a bunch of examples here. And do we have the book link somewhere? Book here. And oh, let me jump back to the slides real quick because I do have a final thought. Yeah, Antje, do you have the slides?
1 sec. I already moved things around here.
I know. Should be it. Okay, actually, I have it.
Have it? Okay.
So, wrapping up, we covered quite a bit today. A lot of good stuff, a lot of good code. And don't forget, if you want to try out the multimodal embeddings by Amazon Titan, show the code here, ImageBind. Join us next month. We're going to have a startup who is doing text to video. They're going to explain everything about how it works and, pretty detailed discussion, and you can ask lots of questions. Text to video is the hot thing, obviously Sora and, Runway ML and those folks. We're also going to have more multimodal. This is an area that I'm actively working with my customers on. So we're going to continue to expand these use cases, these demos. Also putting together a course that'll be coming out later this year. That'll be released on Coursera with one of our partners. So that's sort of on the down low right now, but just kind of giving you folks a heads up that we'll be covering all of this in a nice Coursera package coming up, where we'll be covering all aspects of not just multimodal, but all embeddings and all common RAG use cases. But we will be exploring, of course, multimodal RAG. We're also going to have a talk from one of our friends, me and Antje, have some friends in the product management space that are working on Gen AI projects, and we want to get them and get their thoughts on some sort of unique challenges that a product manager faces when dealing with these, sometimes a little bit fuzzy Gen AI use cases. So yeah, that'll be a really good talk. Yeah, and then join us for the in-person events as well. Antje, yeah, anything else?
I think that's it. Thanks everyone for joining us.
Thanks, everyone. Yeah, have a good week.